Last class we went over experimental techniques for the determination of self and impurity diffusion coefficients. Now next few classes we will talk about interdiffusion. We will study some of the techniques which are used for determining interdiffusion coefficients. We will start with binary systems, and we will also see how the interdiffusion coefficients are determined in ternary and higher order multi-component systems. Most commonly interdiffusion coefficients are determined using diffusion couple technique. In this, two alloys of different compositions are placed in contact with each other. They are held together by some kind of jig, and this assembly is isothermally annealed at some temperature T, at which we want to determine the interdiffusion coefficients. The annealing continues for the desired time, so that good enough diffusion zone is developed which can be analyzed for interdiffusion coefficients. At the end of the annealing, the diffusion couple is quenched from the annealing temperature. The quenching is essential in order to retain the concentration profiles and the microstructures that are developed at the desired temperature T. After the quenching, the diffusion couple is cut parallel to the diffusion direction. One point has to be noted here. To start with, both the alloys are homogeneous. Of course, they have different compositions, but each individual alloy block is homogeneous in composition itself. And for the accurate determination of interdiffusion coefficient, we work with single phase alloys and we work with single phase diffusion couples, which means even after diffusion no second phase is developed in the interdiffusion zone, and both sides of the couple have the same crystal structure or the same phase. After sectioning, the surface is metallographically polished and the composition at each point is determined along the diffusion zone. So, each composition point actually represents composition of the plane going into the plane of board here, and this determination of composition is typically done by electron probe microanalysis using wavelength dispersive spectroscopy, because it gives the most accurate micro composition, and the experimental concentration profiles are then further analyzed for interdiffusion fluxes and interdiffusion coefficients. Suppose we started with two different alloys A and B. Let us first consider binary alloy. So, just one concentration variable is sufficient to define the composition of each individual alloy block. To start with, alloy A, let us say, had a composition Ca minus, and alloy B had the composition Ca plus. After the diffusion annealing, there will be interdiffusion and a concentration gradient will be developed, something like this. Now, this composition profile, as I said, can be obtained by EPMA. Okay. So, the first question is, the first issue here is how do we locate this initial contact plane. Initial contact plane is the plane of contact before the diffusion started. Ideally, if there is a good diffusion bonding that has occurred between the two alloy blocks, this plane would not be physically distinguishable in the diffusion zone. So, what we will see is only concentration profile, something like this. So, how do we identify this initial contact plane, where we assign x equal to 0? That is our plane of reference. So, it is first important to find out that initial contact plane. So, how do we go about this? So, the simplest way is to do the mass balance, because we know the loss of A on the left side of this initial contact plane should be equal to the gain in A on the right side of this initial contact plane. So, whatever A has diffused from left should appear on right. That is the simple principle that we use. So, if we do that, this is Ca minus, this is Ca plus. So, if we consider a small volume element of width dx in the diffusion zone, and if we consider unit cross sectional area, then the volume of this small element would be dx. We want to do the mass balance. Loss on left side should be equal to gain on the right side. So, the loss in this case, if C represents the composition or concentration of A and x is the location of this volume element, let us say, then the loss in this particular element would be Cx minus the original concentration Ca minus times the volume, which is dx. So, this will be Ca minus Ca minus dx, and the loss will be from left terminal all the way to the plane here x equal to 0. Let us call this x naught in terms of the coordinates that we have used for obtaining the profiles. If we integrate this from the left terminal alloy to the plane x naught, we will get the total loss to x naught. Now, remember, when we talk about diffusion couple, most of the time we are dealing with the infinite diffusion couple. For inter-diffusion analysis, in fact, we want infinite boundary conditions to be obeyed, which means none of the diffusant will penetrate all the way through the two terminals of the two alloy blocks. So, in a sense, we can treat the left terminal as minus infinity and the right terminal as plus infinity, and at minus infinity plus infinity, that is at the two terminals, the original concentrations will be maintained. The original concentrations were Ca minus at minus infinity and Ca plus at plus infinity. So, this will be the loss, and the gain similarly on the other side, if we consider any volume element, the gain would be Ca minus Ca plus dx from x naught to plus infinity, and their summation should be equal to 0. Now, if we replace y equal, if we substitute y equal to x minus x naught, we will get dy is equal to dx, and when x is equal to minus infinity, y should be equal to minus infinity 2. Similarly, at x equal to plus infinity, y should be equal to plus infinity, and when x is equal to x naught, we have y equal to 0. So, with this substitution we can write infinity to 0 C a minus d y plus integral 0 to infinity C a minus C a minus C a plus dy should be equal to 0. Now, to simplify this further, let us integrate by parts. For integration by parts, for the first integral, let us assume u is equal to C a minus C a minus. So, remember C a here indicates C a at the position x that is being considered, and dv is dy. So, we have du is equal to dCA and v is equal to y. So, we will get uv Ca minus Ca minus times y, and the limits are for x equal to minus infinity to x equal to 0 minus integral v du minus infinity to 0, v is y and du is dCA. Similarly, for the second integral, we take u is equal to Ca minus Ca plus, dv is equal to dy, and so du is equal to dCA again, and v is equal to y. So, we have uv Ca minus Ca plus times y from 0 to plus infinity minus integral from 0 to plus infinity y dCA. Similarly, for the second integral, we will have u is equal to Ca minus Ca plus and dv is equal to dy, and du is equal to dCA and v is equal to y. So, if we do uv Ca minus times y from, and the limits are for y equal to minus infinity to y is equal to 0 minus integral minus infinity to 0 v du y dCA plus on this side uv is Ca minus Ca plus times y from 0 to plus infinity minus integral 0 to plus infinity v du is y dCA. Now, when y is equal to 0, that is at the initial contact plane, y is equal to 0, this term will vanish. Similarly, at y equal to minus infinity, that is on the left terminal, Ca is Ca minus at all times, and so again this term will vanish. So, this term will be 0. Similarly, this term will vanish at y equal to 0, and also at y equal to infinity, that is on the right terminal, Ca is equal to Ca plus, and so again this term will vanish, and so we have, and this should be equal to 0. So, these two minus signs will go away, and if you see the two integral, they are for the same y dCA, and so we can write integral minus infinity to plus infinity y dCA should be equal to 0. If we substitute for y, we get integral minus infinity to plus infinity x minus x naught dCA should be equal to 0. And this is the equation that we use for locating the initial contact plane here from the experimental concentration profile. This was proposed by Matano So, this plane x naught is also referred to as Matano plane. Now, we need to note 2 points here. First, we obtained this equation independent of number of components, which means whether we are considering binary couple, ternary couple or quaternary couple, this should be applicable. But there is also other condition with it, because we want to use this plane, we want to use Matano plane as the reference plane for finding out interdiffusion fluxes and interdiffusion coefficients. And so, this plane has to be same for all the components. So, no matter which component we use for finding the location of Matano plane, we should get the same location, and this is possible only if all the components have constant partial molar volumes. If the partial molar volumes of the components is function of composition, then with diffusion there will be net expansion or shrinkage of the couple, and therefore, each individual component will yield different location of this plane. So, the second condition, so the condition applicable for this is that the partial molar volume should be independent of composition for each diffusing element. Okay, so we got the reference plane. Now, what next? We need to find the interdiffusion coefficient from here. So, we found the reference plane, which we can do based on this equation. So, how do we go about this? If we again write this equation, if we split this integral at x naught, we can write minus infinity to x naught, x minus x naught dCA plus integral x naught to plus infinity x minus x naught dCA should be equal to 0, and this integral is nothing but the area under the curve plotted onto the plane x naught. So, if we look at this figure here, the integral from minus infinity to x naught, that is from minus infinity to x naught, here it is the area under the curve plotted onto this x naught. So, it represents this area. Let us call this area P. So, this is area P, and what should be the sign for this area? Remember, x minus x naught is negative on the left side, and dCA as we go from left to right is negative. So, the sign should be positive, and this area x naught to plus infinity, and this integral from x naught to plus infinity is the area under the curve again plotted onto the Matano plane. So, x naught to plus infinity. So, it represents this area, let us call this as Q, and the sign of the area would be x minus x naught is positive on the right side and dCA is still negative. So, the sign would be negative. So, P minus Q is equal to 0, which means area P should be equal to area Q. So, area P on the left should be equal to area Q, and this is how we can locate the initial contact plane, or which is also referred to as Matano plane. Now, we have fixed the reference frame here with the assumption that partial molar volumes of all the individual components are independent of composition. Next, we need to find out the interdiffusion coefficients. That is our goal, main goal here. So, let us consider this concentration profile again here. So, we have Ca minus as concentration on left side, Ca plus as concentration on the left terminal, and we know diffusion equation dou C by dou T at x should be equal to minus dou J tilde by dou x at T, and when we are considering the practical system, the interdiffusion coefficient d tilde is function of composition, and so we have to write this right hand side as dou by dou x of d tilde times dou C by dou x, and since we are referring to component A, let us call this J A tilde and C A. Of course, we are referring to the binary interdiffusion here, which needs only one interdiffusion coefficients for both component A and B. We need to solve this equation for d tilde, and d tilde is varying with x. So, we will use the approach proposed by Boltzmann here. We know when d tilde was constant, we solved this equation analytically, and we know that C is a function of x over root t, where x over root t is equal to lambda, which is known as Boltzmann parameter. Boltzmann proposed that this should also be true when d tilde is varying with composition, and this has been actually proved in practical diffusion couple in practical systems, that C is a function of lambda. What does that mean? So, if we anneal the same diffusion couple at the same temperature, let us say for 3 different times, we will get different composition profiles like this, and if we track any particular composition plane, let us say C A here, if we track its position at 3 different times in the diffusion zone, let us call those as x1, x2 and x3. The 3 times we call T1, T2 and T3. Lambda is constant for a given composition. So, we can write x1 over root T1 equal to x2 over root T2 equal to x3 over root T3 should be equal to constant lambda, and lambda is a function of C. Now, we would transform this partial differential equation to ordinary differential equation using the Boltzmann transformation by using this Boltzmann parameter lambda equal to x over root t. Let us see how we do that. Since lambda is equal to x over root t, we know dou lambda by dou x should be equal to 1 over root t, and dou lambda by dou t should be equal to minus x over 2 t to power 3 by 2, which is t root t. Now, if we look at the left hand side, dou C by dou t, we can write this as dC by d lambda times dou lambda by dou t, constant x, and we know dou lambda by dou t is minus x over 2 t root t. So, dou C by dou t at x, which is the left hand side of this equation here, should be equal to minus x over 2t root t dc by d lambda. Note, we are writing the derivative of c with respect to lambda as ordinary derivative, because c is a function of lambda. Lambda involves both the parameters x and t. Similarly, dou c by dou x at t we can write as dc by d lambda times dou lambda by dou x at constant t, and we know dou lambda by dou x at constant t is 1 over root t. So, this should be equal to 1 over root t dc by d lambda, and if we substitute in the diffusion equation here, we will get minus x over 2t root t dc by d lambda should be equal to dou by dou x of 1 over root t d tilde dc by d lambda. Now, this is at constant t, so we can take this 1 by root t outside. We get minus x over, and if we take 1 by root t outside, it will get cancelled. Minus x over 2t dc by d lambda of d tilde dc by d lambda. Now, this again we can write as d by d lambda of d tilde dc by d lambda times dou lambda by dou x, and dou lambda by dou x is again 1 by root t. So, if we substitute for dou lambda by dou x, we get minus x over 2 root t dc by d lambda should be equal to d by d lambda of d tilde times dc by d lambda, and if you multiply both sides by d lambda, we end up getting minus x over 2 root t dc should be equal to d of d tilde dc by d lambda. Now, if we substitute back for dc by d lambda, we get from here dc by d lambda is equal to dou c by dou t at x divided by dou lambda by dou t at x. For the fixed diffusion annealing time, if we integrate both sides from the left terminal to the desired x, we can write integral, since t is fixed, we can take this out, minus 1 by 2 root t integral from integral c minus to c at desired x of x dc should be equal to, now if we see on the left terminal alloy, the value of d tilde times dc by d lambda would be equal to 0, and at c at x it should be equal to d tilde at that particular composition which is at x times dc by d lambda. So, we write this d tilde at x times dc by d lambda. Now, we can substitute for dc by d lambda. So, from here dc by d lambda is nothing but root t times dou c by dou x at constant t. So, this should be equal to root t times d tilde times dou c by dou x at given t. And since we are considering the composition profile after a fixed diffusion annealing time t, we can replace this with dc by dx, that is the derivative of concentration profile. And so, if we rearrange, we get the equation for d tilde at x, and since d tilde is actually function of Ci and Ci is varying with x, and that is why d tilde is varying with x. So, we should write appropriately as d tilde of the composition C should be equal to minus 1 over 2 t integral C minus to C at x, and if we denote the reference plane as x naught, just like there, then it should be actually x minus x naught dc divided by dc by dx at the position x that we are considering, and this gives the equation for binary interdiffusion coefficient. Now, what is this integral again? It is nothing but the area under the curve. So, if we consider this concentration profile again, remember we were talking about the concentration of A, and then we dropped the suffix because we are considering the binary system here, and for binary system to define any composition we just need one concentration variable. So, C implicitly we are assuming here it is Ca. So, to find out this integral is nothing but the area under the curve. So, if we want to find out d tilde at position x, some position x prime, let us call x prime here, then we evaluate this integral. That integral is nothing but the area under this curve drawn onto the Matano plane. This is x naught, or what we call as Matano plane, and this is nothing but the integral c minus to c at x, x minus x naught dc. Then we determine derivative of the concentration profile at this position, which is the dc by dx, and we know the diffusion annealing time t, and so we can find d tilde at this particular location, and it corresponds to the composition which is there at this location, that is C at x. Now, it can be easily seen this we can apply at any plane in the diffusion zone, and so we can find out interdiffusion coefficient at every composition that develops in a binary diffusion couple using this technique. And this technique is commonly known as Boltzmann-Matano analysis. So, this is how we can get binary interdiffusion coefficient from a single diffusion couple experiment. We can determine interdiffusion coefficient at every single composition that is developed within the diffusion zone of that couple. Now, how do we extend this to ternary and higher order diffusion couples? That we will see in the next class. Thank you.